This is your friendly neighborhood physics teacher here, and we're going to talk about mechanical energy. Another word for mechanical energy is total energy. So your mechanical energy is just your total energy. Mechanical energy is just your total energy. Now, and your mechanical energy is all your energies added up. So basically, it's your potential plus your kinetic. Now, for your potential can be your elastic potential, and it can also be gravitational, or it could be both. You can have multiple potentials in there. You can also have multiple kinetics. If you have two objects that are moving, you might have multiple kinetics. But just an overall, we say your mechanical energy, your total energy, you have to add up all your potentials and all of your kinetic energies. Now, for a closed system, what a closed system means. For a closed system, all that means is energy is truly conserved. Energy is conserved for the system. And kind of like everyday speak, no energy in or out. So the amount of energy you put into the system you put into the system is equal to the amount of energy you get out of the system. The amount of energy you put into the system is the amount of energy you get out of the system. So simple equation for that. Now this mechanical energy is the first equation that we've come across that's not in the formula chart. That is a concept, because basically they're saying, well, you should know that your total energy, you have to add up all your energies. So I'm going to add up all energies, basically. That's all that is. So basically we're saying that our amount of mechanical energy before has got to equal the amount of kinetic energy after. So before whatever happens, it's got to equal after whatever happens. So it's like if you're about to drop a ball, so what's the amount of energy before you drop the ball? It's got to equal the amount of energy after you drop the ball. And it's got to equal the amount of energy as it's being transferred, so on and so forth. Another way to look at that is just your initial equals your final, or you can also see that your initial as a naught equals your final. So those are the multiple ways you can kind of see it. And there's different kind of scenarios that we could be given to solve for this. So let's kind of do some practice problems. So these are practice problems. And these are going to be more conceptual, so there's going to be no numbers. This is just going to be purely kind of like what to expect. So practice problem number 1. We're going to look at, this is a ball. You have a ball. Ball. The ball is being held, let's say, some distance above the ground. The ball does have some type of mass. And we want to figure out what type of velocity said ball would have right before it hits the ground. So right before it hits the ground. So again, we can think about our mechanical energy before I drop it has to equal the mechanical energy after I drop it and right before it hits the ground. So what type of energy does it have at the top? Well, hopefully you said it had gravitational potential, and that's it. So I know your mechanical energy is potential plus kinetic, but if it's not moving, it doesn't have any kinetic energy. So before, it just has gravitational. That has to equal, well, at the bottom, there's no height. So it's just kinetic. So this is where your potential at the top equals your kinetic at the bottom. This only works for a closed system. Now, if I picked any other height in the mix, yes, we would have a potential and a kinetic. So in that case, we would have gravitational at the top would equal our gravitational plus our kinetic, which has to equal our kinetic at the bottom. This is when our mechanical energy is constant. A little thing we can add to this up here in our notes. Our mechanical energy is constant. It does not change. Our total energy does not change. So it doesn't matter at any point in time when this ball is falling, if I say find the total energy, it would be the same. It would be the same. So yeah. So that's kind of a falling system. So let's look at another practice problem. So number 2. Let's look at one let's look at a spring. Let's use some spring potentials. So if we have a ground, we have a mass with a spring. And let's say I stretch, like I physically take it and I move the mass. I stretch the mass, or stretch the spring to there. From here, oops, let's do a different color so it doesn't blend in. From here to here will be our x. You remember our x is how much the spring was either extended or how much the spring was compressed. So in this case, it's how much it was extended. We still have some type of mass. Our mass still has a mass. And our spring has its own very spring constant. And remember, spring constant is a unique constant. Spring constant is constant for this particular spring, but if we change springs, the spring constant will change. So it's not like gravity, which is always 9.8. A spring constant changes with the item. But we're not changing springs, so it's constant for this situation. Now, so I'm sitting here and I'm holding let's see a horrible chance for a hand here. 1, 2, 3, 4. So I'm holding this block. Woohoo. Okay. So I'm holding that block. If I let that block go, it's going to go back to where it was and even go a step further of being scrunched. And what's really cool, from here to here is going to be the same x. So we're saying that the block is moving this way now. So it's moving. So right here, this would be the mechanical energy before. This will be the mechanical energy in the middle. This will be our mechanical energy after. This middle line is called our equilibrium. That middle line is called our equilibrium. At the equilibrium, there's no elastic potential because the spring's not being stretched. That's its happy spot. So there's no potential there. It's all kinetic. So if we were looking at our mechanical energy before, now remember, all these have to equal each other, equal our mechanical energy in the middle. I'm just going to put middle. Has to equal our mechanical energy after. So as I pull and I'm holding it right here for our mechanical energy before, that's going to be nothing but elastic potential. When it gets to equilibrium, it's moving its fastest, so it's going to be nothing but kinetic. And then as it scrunches again, it's going to go back to being nothing but elastic. So this one is a complete even transfer. It's going from elastic potential, because I've stretched it out. In the middle, it's moving its fastest. So at equilibrium, you're going to have all kinetic, and then you're going to have, again, elastic. Now, of course, because your mechanical energy is constant, in anywhere in between, you would have a kinetic plus your, I want to say before, middle, after. Anywhere in between, you would have some type of combination that equals to your mechanical energy. It would all equal each other because your mechanical energy is constant. So that's kind of a example 2. Another example would be like one with all 3 of them. And for that one, we're going to do a spring hanging. Okay. So we're going to talk about a spring hanging. So again, this would be our equilibrium. So that would be our equilibrium that's in the middle. Now remember, at equilibrium, there's no elastic potential. There's no elastic potential because it's not being stretched. That's just where the spring wants to be. We do have some type of height. Hold on. Not there. So we have our y initial, our y before collision. We have our y in the middle again. And then here we would have our y after. So we have y's. We do have x again. So that's x. That's x, and it's the same. So again, so think about, so we have, again, the spring. So I've grabbed the mass. And I'm holding it here. My hand looks funny, that's okay. So I've grabbed the mass and I'm holding it here. As soon as I let go, the spring is going to go up. It's going to hit equilibrium and then keep going. So now we have to think about what type of energies is happening. There's all kinds of different types of energy that's happening right now. So we still have your mechanical energy before, which would be this part here. It's got to equal our mechanical energy in the middle. It's got to equal our mechanical energy after. So before, so while I'm holding it, what type of energies is happening? Hopefully you said elastic and gravitational. So that's elastic before and gravitational before. Because it has some height, so it has gravitational in the mix. And that has to equal, so this is at equilibrium, there's no elastic, so we have kinetic plus our gravitational, and that's at the middle. And then that has to equal, again, our elastic potential after plus our gravitational after. So all of that has got to equal each other. So that's what I'm talking about. You have to add up all of your energies. You have to take all of your energies into consideration. And since it's a closed system, everything equals. Energy is conserved. So those are some good three basic practice problems. You can see just with gravitational and kinetic, one with elastic and kinetic, and then one with all three. Hope that kind of helps. If you have any questions, please ask. Have a wonderful day. Bye.